Welcome back, everybody. So I do not have problem number 1 up on my screen because it was handwritten on your page. So I'm just going to go through those. And again, I'm going to go through as much as I can in the time that we have here today. Right.
As long as we can get to like the last.
Yeah.
All right.
And number 10.
The back page, yes, is
Basically,
good.
let's like start.
I'm
with
gonna,
the
you know,
whole
I'm gonna do what I
discussion.
can with what I have where I am. Right.
That's
a good idea.
You said that,
Good idea.
Teddy.
Roosevelt?
Yeah.
Oh, wow. I should have known that. I really am.
Just saying.
How did you not know that?
All right, so let's go quick here. Number 1 here. Find the locations of the local and absolute minimums and maximums. All right, so if I want the absolute max, where does that occur? What's that look like?
6.
6. What's the absolute min? 4. So local mins. Looks like I've got a negative 1, 2, 3. Negative 1 is a local min. Yes, we all know that, right?
Yes.
Negative 1 is a local minimum because that point at negative 1 is lower than all of the points around it. And then it looks like a positive 1 is a local min, and then obviously positive 4 is also local min because it's also absolute min. Local max, 2. Is that it?
Yeah.
Just 2?
Yeah.
That's it. Okay. Are there any questions on number 1? No? All right, number 2, find the critical points up here. And remember, this is a 2-day test, so there's somewhere in the neighborhood of 14 questions, so that you can plan on halfway through that is the break in the day. So whatever's not on day 1, obviously, is definitely going to be on day 2. So remember, finding the critical points. Let's remind ourselves, the critical points are where the zeros of f prime of x are, and where f prime of x does not exist. See, normally we just focus on the zeros of f prime of x. But because this is a rational function, I've got to think about, okay, not only the zeros, but also this could not exist in certain places. So let's find our critical points by first off taking f prime of x. Okay, so f prime of x. Oh, this is a quotient. I got to use quotient rule. F prime g minus g prime f all over g squared. Right? So f prime, derivative of x minus 1 is just 1. So x squared minus x plus 1 minus the derivative of g is 2x minus 1. Derivative of the bottom is a 2x minus 1, and then times, don't do that. Just want to move you. There we go. Times the original numerator, f, x minus 1, all divided by x squared minus x plus 1 squared. Does everybody follow me on just the quotient rule?
Yeah.
F prime g minus g prime f over g squared. And then let's FOIL. So we got x squared minus x plus 1 minus, and I'm going to leave this in parentheses, 2x squared. Ninja. I didn't see him until like the last minute there. Minus 2x minus x plus 1 all over g squared, whatever. And then so f prime of x is equivalent to, okay, I've got an x squared minus 2x squared. So negative x squared. I've got a negative x, and this is a total of a minus 3x. But when I distribute that negative in, that's a plus. So plus 2x, right? Because that's negative 1, right? Negative 1 and then a positive 3, basically. Right? Negative 1, positive 3 makes 2. And then positive 1 minus 1, that just cancels out, over the x squared minus x plus 1 squared. So that's the derivative. All of that work was just to find the derivative. And now at this point, I want to find the zeros of the derivative, because that's the first set of critical points. Now the zeros of the derivative is where the numerator equals 0, right? Think about a rational function. Where does it hit the x-axis? where the numerator equals 0. So negative x squared plus 2x is 0. I factor out the negative x, leaving an x minus, you don't have to factor out a negative x. I factor out the negative x, leaving an x minus 2. So negative x equals 0. X minus 2 equals 0. So x equals 0. X equals 2. Okay, those go on my answer blank. But I can't stop there. Because this is a rational function, the derivative could not exist where the denominator equals 0. So I have to set the denominator equals 0. X squared minus x plus 1 squared equals 0. Now, okay, to undo this may seem like, oh man, I got to square that whole thing. No. If I square root 0 over to the other side, it's just going to be 0. So this is essentially the same thing. Okay? Like the sound effects?
Mm-hmm.
Thanks. Now, can I factor that though? Bummer. I can't factor that. So I've got to do something different. Well, I guess I could complete the square if I'd really like to, but you guys would probably throw things at me. Let's do the quadratic formula. The opposite of b plus or minus the square root of b squared minus 4ac all over 2 times a. Well, look at the discriminant here. Inside the radical, what's going to happen? Well, this is going to be a negative 1 squared, so 1, minus 4. A negative 3. So this would be 1 plus or minus the square root of negative 3 over 2. Are there any real solutions to that? No. So is there any place where the denominator equals 0? Nope. The only 2 critical points would be 0 and 2. I did basically all of that work for nothing right there, right? But I needed to do it to really say that there are no places where the derivative does not exist. We looked at the zeros of the numerator to find where the zeros of the derivative were, but the derivative could not exist, may not exist, where the denominator equals 0 as well. So got to check that. Got to go through that process. Because that's non-real, I can stop at that point and say, nope, that's not going to happen. I'm done there. Yes?
If that was a real number, would that be another critical point?
Yeah. So say this was not x squared minus x plus 1, but maybe, okay, so now going off on a tangent, no pun intended, derivative. Say this was minus 3x minus 2, right? Well, then that would factor, right? X minus 2, oh no, so that's a plus. Let's say that's a plus 2. X minus 2, x minus 1, right? So then I would have to say, okay, x equals 2, x equals 1 would be more critical points. Now, I accidentally made that the same thing, but you get the idea. Yeah? So you must also take into account where the derivative may not exist down there as well. Make sense? Zeros, where the derivative does not exist. Basically, you're finding the zeros of the numerator and the denominator, honestly. Because that's where the numerator, that's where the zeros or the critical points. All right, same thing here. Find the critical points of ln of x squared plus 3x plus 2. Okay, so for this one, I've got to figure out where the derivative may not exist or where the zeros of the derivative may be. Again. Okay. See, this is going to come into play here. Actually, coincidentally enough, didn't I make that the exact same thing? Oh gosh. Look at that, x squared plus 3x plus 2. I almost made this like the exact same thing on my hypothetical. Weird. Anyway, when I find the derivative of this, okay, ln of x, Remember that this is like saying, it's kind of like a chain rule type thing, where I find the derivative of ln, which is 1 over that thing, right? Well, what is that thing? X squared plus 3x plus 2. And on the top, I would multiply by the derivative of the inside. Okay? So this is essentially 2x plus 3 over x squared plus 3x plus 2. There's my derivative. Right? There's my derivative. And when I go to find the critical points, I say, well, the zeros would be where 2x plus 3 equals 0. The do not exist points would be x squared plus 3x plus 2 equaling 0. Okay, so that means subtract the 3 divided by 2. X equals negative 3 halves, or negative 1.5. Right, yep. And then where it does not exist. So that does factor x plus 1, x plus 2. So x equals negative 1, x equals negative 2. All 3 of those are critical points. So that is an actual example where the denominator comes into play, or be real. Questions on that? All right, let's take a look at 4. Use the closed interval method to find the absolute maximum and minimum values of the function on the given interval. So basically what I'm asking you to do here is create for ourselves a table of values. We want negative 2 and positive 3 to be in that table, and we need the critical points in between there to be other parts of our table. All right, the critical points, excuse me, would be f prime of x is 12x to the third minus 12x squared minus 24x. Factor out a 12x, it looks like. And that's an x squared minus x minus 2 equaling 0. So I know that I have an x equals 0, so I can put that in there. Well, I guess I better keep them in order. And then we have a factor that. Factors a negative 2 to get to negative 1. Negative 2, positive 1. So we have x equals 2, x equals negative 1. So we have negative 2, negative 1, 0, 2. Okay, so a lot of candidates that could be the absolute maximum or minimum values. Got to check the endpoints as well, though, right? Now, where do I plug these into? Do I go back into the derivative or the original? Original, good. I was worried that someone was going to say the derivative. Because that, if I'm plugging it back into the derivative, that's that increase-decrease test. Okay? That's not the same as the closed interval method. Okay? This goes, basically what we're doing here is, these are the x values. Find the y values that are the biggest and the smallest. Yes?
So you only plug it back into the derivative if you found the second derivative, if you found the second derivative test?
No. You only plug it back into the derivative when I do like the number line test.
Mm-hmm.
That's when you go back into the derivative.
Okay.
This closed interval method is just basically saying, these are the possible x values that would be biggest or smallest.
Mm-hmm.
See what they come out to be to say whether they're biggest or smallest. All right, so I hope you don't mind. I'm just going to cheat off my key. Negative 2 comma 33, negative 1 comma negative 4, 0 comma 1, 1 comma, I didn't have 1 comma. What is 1 comma what? Oh, there is no, oh, I crossed 1 out, that's why. 2 comma negative 31 and 3 comma 28. Right, all I did for those is just plug it back into the original. Forgive me for being lazy. All right, so absolute max is negative 2 comma 33. Absolute min, 2 comma negative 31. Oops, that's absolute min. Questions about that? All righty, let's look at 5. State the hypotheses and conclusions of both Rolle's theorem and mean value theorem. Write the algebraic conclusion for the mean value theorem and state it in your own words. Ooh, that's fun. Kind of adding a new layer onto the question from the quiz, aren't I? Because the question from the quiz was basically, all right, Rolle's theorem and mean value theorem, compare and contrast, right? Okay, so hypotheses for Rolle's and then MVT. Okay, so for hypotheses, they both have to be continuous and differentiable. But for Rolle's theorem, you have to have f of A equaling f of B. Mean value theorem does not. Conclusions. All right, conclusion says that there must be some value, f prime c, where it equals 0. Mean value theorem does not say that. Mean value theorem says that, okay, there must be some value f prime of c such that it equals the slope, f of b minus f of a, over b minus a of the endpoints. And essentially that's the equation, right? When it says state the algebraic conclusion of the mean value theorem, that is f of b minus f of a is equal to f prime c times b minus a. Sorry for, whoa, that you're not going to be able to see that on TV. It's a little cut off there. That's a b minus a. Oh, I should really scoot and rewrite. F prime c quantity b minus a. There we go. That's a little bit better. There's a prime in there. That's a prime, f prime c. Now, in our own words, what does that mean? That means that there must be some value for the mean value theorem. That's what I'm talking about. Mean value theorem. There must be some value in between the endpoints that is equivalent to the slope of the two endpoints, right? There must be some value in between the endpoints. Somewhere in the middle, where the slope of that point, the tangent line, is equivalent to the slope of the endpoints. You know, I think in class, didn't we have that example where we were saying something like, you know, if you travel from here to Columbus and the speed limit is 70 miles per hour or whatever, and you get there with an average speed of 75 miles per hour, at some point, you must have been speeding, right? Because at some point, the average of the two endpoints, the average of the whole trip, you must have gone at that point, at that speed, some point along the way. All right, questions on that? Okay. Number 6, verify that the functions satisfy the hypotheses of the mean value theorem on the given interval. Then find all numbers c that satisfy the conclusion. All right, so this is another one of those ones where you have to state the reasons why it is, why it satisfies, right? So it's both continuous and differentiable. Because this is a polynomial. Right? This is a polynomial, so we know it is continuous and differentiable, so therefore the mean value theorem applies. I'm not talking about Rolle's theorem where you have to find f of a is equal to f of b. This is just the mean value theorem. Then find all numbers c that satisfy the conclusion. Remember, the conclusion says that f of b minus f of a is equal to f prime of c times b minus a. Basically, f prime c must equal the slope at some point of the endpoints. So that c must be in there somewhere. All right, so we got to find f prime of c. So f prime of, let's put c in real quick. Let's put f prime c. 3c squared minus 3. That's it. Right? 3c squared minus 3. I change it from an x to a c because I'm saying at some point there is a value c in between b and a. All right, so so b is 2 and a is negative 2. I've got to find f of negative 2 and f of positive 2. All right, let's go back in. Negative 2, I'm just going to be a little cheater again. F of negative 2 is 0. Again, we're going back into the original, not the derivative. F of positive 2 looks like it is 4. Okay, just plugging that back into the original to find those values. So F of B, so this is A and B, right? First term, last term, A and B. So F of 2 is 4. F of A is 0. Minus F prime C, 3C squared minus 3, times B minus A. So 2 minus a negative 2. And then we say 4, 3C squared minus 3 times, hey, 4, right? 2 plus 2 is 4. All right, let's divide that over to the other side. Let's divide by 4 over. Instead of distributing it, let's divide by 4. 3C squared minus 3. So this is 4. Ooh, this is a weird answer. So plus or minus the square root of 4/3 is C. And I think both of those, is that true? Yeah, I put plus or minus 2 over radical 3. The same thing. And I guess the only thing I should check to make sure that it's in our intervals, right? I'm bothering about negative 2 to positive 2. So let's test out square root of 4 over 3. Does that come out to, yeah. So it would be 1.15 and negative 1.15, which is in between our intervals, negative 2 to positive 2. Okay. Let's keep it moving. Number 7, find the intervals on which the function is increasing and decreasing. Use that information to find the local maximum and minimum values. Do not use the second derivative test. Give the full coordinate for the extreme values. I'm going to shut the door. All right. Find the intervals on which the function is increasing or decreasing. Well, to do that, that's at the critical points, right? So f prime of x is 3x squared minus 6x minus 9. Factor out the 3. X squared minus 2x minus 3. So that means I've got an x minus 3 and an x plus 1. So 3 and negative 1, right? Sorry, I'm trying to go fast to get to all the problems. So. Okay, increasing, decreasing test does this. Negative 1 to 3, and let's pick some points. Okay, let's pick negative 2, 0, and 4. Now, this goes back into the derivative, right? This is where we go back into the derivative with those testing values. So this means I've got 3 times negative 2 squared minus 6 times negative 2 minus 9. Positive. 0 goes in, that would be a 0, negative 9. Oops, don't care about the 9, I just care about its negative. And I'm guessing that when I plug 4 in, it's going to be positive, but let's double check it. 3 times 4 squared minus 6 times 4 minus 9. Positive. Hey, look at that, 15 as well. So that means it's increasing, decreasing, increasing, right? Increasing to decreasing to increasing. So that means, that would be, this is a increase to decrease. Local max at negative 1 comma something, and then it goes decreasing to increasing, local min at 3 comma something. Now, to find the y values, I go back into the original. So that would be negative 1 comma negative 1 comma 9, and then 3 comma negative 23. So if I say find the intervals of where it's increasing or decreasing, I would say that this is increasing on the interval negative infinity to negative 1, and then again from 3 to infinity. Remember, go to your critical values. Don't use your testing ones that you just picked out of thin air. Decreasing would be from negative 1 to 3. Yes, sir?
So to find the y values, you put the x values of the local ones to the original.
To the original, right. You're just basically finding where that's happening on the graph.
But then for the graph, you put them into
Yeah, for the number line, you're just testing to see whether on each side of this are all points increasing or decreasing. So you go to the derivative to do that. Okay, would you all agree that 8 and 9, 9 is the second derivative test thing. I think you would agree that 8 and 10 are very similar. And 10 is a lot more difficult. So I'm going to skip 8 and do 10 in a minute. Okay? If we have time, I'd love to come back and do 8, but I think 10, you guys would benefit a little bit more than 10. So I'm going to do 9, and then I'll hit 10. Use the second derivative test to find the local maximum and local minimum points. All right. Now, second derivative test says this. I'm going to reorder this. F of x is 3x squared minus 2x cubed plus 1. Did I make this so that it would come out weird again? I hope not. Nope. I think it's good. All right. So first derivative is this. 6x minus, sorry. Why did I write it like that? That was stupid. Negative 2x cubed plus 3x squared plus 1. All right, so f prime is negative 6x squared plus 3x. Right? F double prime of x is negative 12x. Now, remember, plus 3. What? Just test to make sure you're paying attention. Thank you. Thank you. I almost forgot the plus 3. Oh, now that should be a plus 6, shouldn't it be? That should be a plus 6 now. There we go. Fixed. Now, where should I go to find the critical points? F prime, the first derivative, right? Here is where the critical points are. Please don't go here. What are you finding if you find the zeros of that? Inflection points, right. Look at you guys go. Proud of you. Okay, so factor out the negative 6x. X minus 1, so x equals 0, x equals 1. Now, my second derivative test says this. I don't know why I did that. I have really weird sound effects.
That was
That was a new one.
I find f double prime of 0, I get 6. Do I care about the fact that it's 6? No, I care about the fact that it's positive, which means that it's concave up, which means that it's a local minimum point at 0. Okay, f double prime of 1, I plug in 1, negative 12 plus 6 is negative 6, which again is negative, which means it's concave down, which means it's a local max at 1 comma, and I'll cheat again, 0 comma 1, 1 comma 2. That makes sense? So again, when you're using the second derivative test, you find the critical points the same way you would do it if it's the increase-decrease test. But then you put them into the second derivative to see whether it's concave up or down. Because when you know it's concave up or down, that's when you know whether it's a local maximum. Questions on that one? Okay, this next one is a fun one. Me gusta. What if I taught in Spanish? Like, what if? Imagine going into a math class that was taught in Spanish.
I feel like we've had this discussion before.
Have we talked about this? I think about that all the time. Like, because I have my German foreign exchange student right now, and like, wow, just to,
She was in a physiology class.
I know. I think she's way above Algebra 1, but like they didn't know where to put her. Because like, again, the math is probably not over her head, but maybe me talking, you know.
This has to be so hard.
Find the intervals of increase or decrease. Find the local maximum, minimum values. Blah 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 blah. Just graph, right? Okay. So I am going to manipulate this. What's another way to write 1 over x? X to the negative 1. And I'm going to use that to help us along our way. Okay, so f of x is equal to 1 plus x to the negative 1 minus x to the negative 2. Because it's so much easier to find the derivatives when we treat it like that. Yeah. That's that part right there. If you didn't figure that out, then it's like, oh, what the heck do we do? Right? All right, so that means f prime of x is going to be equal to, okay, that goes away, right? The 1. So negative 1 x to the negative 2. Again, keep dropping down in value. And then this is going to turn into a plus 2 x to the negative 3, because negative times a negative is positive. At this moment, I'll just keep it rolling to do f double prime, because we'll need it in a second. So this is going to be a positive 2 x to the negative 3 minus 6 x to the negative 4, right? All right, critical points. Now, I want to find the zeros. Negative 1, or just negative x to the negative second plus 2 x to the negative third equals 0. I think this is the best way to solve this. Let me just see. Yep, this is what I would do. Let's add this x negative x to the negative second over to the other side. 2x to the negative third is equal to positive x to the negative second now. How would I get this x to the negative third to go over to the other side? Divide it, right? Okay. So 2 is equal to, what are we going to do with the exponents? Subtract them, right? Negative 2 minus negative 3 is positive 1. Look at that. X equals 2. Now, that's the zeros. Wait a sec. Isn't that just like 1 over, or negative 1 over x to the second? Right? What happens if I plug 0 in here? What happens if I plug 0 in here? Because another way to rewrite this would be like saying negative 1 over x to the second plus 2 over x to the third. Can I have 0? No. Because 0 does not exist. Okay, so x equals 2 and x equals 0 are my critical points. Okay? X equals 2 is my zeros. X equals 0 came from because this was undefined at x equals 0. Okay? We good? Huh? Okay, so now I do my number line test. I'm at 0 and 2. Okay. Let's go negative 1, positive 1, positive 3. And we go back into the derivative. All right. Negative 1 times negative 1 to the negative second plus 2 times negative 1 to the negative third. Negative 3. So this turns out negative. Let's take a look at 0 and 1. let's take a look at 1, between 0 and 2. I'm going to do this exact same thing, but instead of all the negative ones, I'm going to use positive ones. Positive. And then what do you think is going to happen at 3? Let's test it though. Perfect. Okay. Negative. Just what we thought. Okay, now, when I go to graph this, I guess I should now look at my inflection points, right? Let's find the inflection points. 2x to the negative third minus 6x to the negative fourth equaling 0, right? All right, let's do that same thing where we, let's add that 6 over to the other side because it's negative. 2x to the negative third is equal to 6x to the negative fourth. Let's divide by x to the negative fourth. Negative 3 minus negative 4 is, again, a positive 1. So 2x equals 6, so x equals 3. But again, also, x equals 3, but also x equals 0, because you not only have to consider the zeros, but also where this may not exist. Okay. So number line test here between 0 and 3. Well, if I go back into let's do a negative 1 again. 2 times negative 1 to the negative third minus 6 times negative 1 to the negative fourth is negative. Let's take 1. Let's between 0 and 3. Let's go 1. So 2 times 1 to the negative third minus 6 times negative 1 to the negative fourth. Ooh. Weird. Spoiler alert, the next one's positive. To save time, I'm just going to, just trust me. That one's positive. Okay, so that tells me everything I need to know. So let's go through each piece that it asks me. Well, it asks me to do the intervals of concavity. Increase, decrease. So I'm going to put all the answers in green. So this is increasing. Where? From 0 to 2. It's decreasing from negative infinity to 0. And then again from 2 to infinity. There is a local max. At 2 comma, and just for our purposes here, believe me, it's 1.25. Now, my local minimum, decreasing to increasing, would be at 0, right? Wait a sec. What would happen if I plugged in 0 to my original problem?
0. 1.
Does not exist. Because 1 divided by 0 is nothing. It's like does not exist, not 0. Yeah? So, something weird is happening there, right? Wait a sec. If it's 1 divided by 0, doesn't that mean that's the vertical asymptote at that place? So, is there a local minimum at that place? No. It does not exist there. Okay? Because if I tried to plug 0 back in, doesn't work. Does not compute. And then we have concave upward. Okay, so that was 3 to infinity. Concave downward. This is concave downward all the way from negative infinity all the way up to 3. my inflection point. Is there an inflection point at 0? No, because there's nothing at 0, right? If you try to plug in 0, it does not exist. The inflection point is at 3 comma. And in my key, I only gave x equals 3. So we'll just say 3 comma something. And we will graph.
This is hard.
Yeah. It's okay, though. It's all right.
I feel like I understood it more.
Okay, so
Well,
we've
that's
got...
because this one was a lot easier.
Yeah. That's true. Let's take a look at this one now. So we got, looks like it's a maximum at 2 comma 1.25. Okay. 2 comma 1.25, somewhere right there. There is an inflection point at 3. And I know it's downward to concave upward, right? And then I know that this is still concave downward, and there's at 0. Now, think about it. It was increasing from 0 to 2, but then decreasing from negative infinity to 0, right? That's why this is going upward here. But this is going to be decreasing from negative infinity to 0. So it's always going to be going downward here. Always going to be going downward. And it's also concave downward because it's negative infinity to 3. Every point from negative infinity to 3 is concave downward. So there's our graph. I agree, that one was kind of that was a nasty one. All right, we got 5 minutes left. For this one here, and I'll post the key as well. For this one, use the increase-decrease test to show that the function has a critical point. Yes?
That last question, what was the y value of inflection?
I don't know. I did not have that in there, but you could just plug that into the original. Just plug 3 into there and see what happens, and there it is. For number 11 there, it says use the increase-decrease test to show that the function has a critical point. That is not an extreme value. Okay, to find the critical point, I would need to find the derivative of that, right? All right, so f prime of x. Anybody know what I have to use? Chain rule. 3 times this thing squared times the derivative of this thing. What's the derivative of the inside? 2. So f prime of x is equal to 6, 2x minus 14, distributed into 6. Oh, squared. Squared. Oh, that's easy. I don't even have to FOIL that. 6 times 2x minus 14 squared equals 0. If I divide the 6 over, excuse me, I still get 0. I square root 0. I still get 0. So x is equal to 7, really, right? That's my only critical point. Okay, so on the left side of 7, maybe 0. If I plug in 0, I get negative 14 to the 3rd power, which is negative. If I plug in 8, let's see what happens with 8. 2 times 8 minus 14. Oh, I'm sorry. I'm going back into the, I accidentally going back in there. Hold on a sec. I made the mistake. I went back into the original, not the derivative. Go back in here. I get negative 14 squared is what? Positive. not negative, positive. Go back into my derivative, right? Plug in 0 here, negative 14 squared is positive. And then now if I go in here again with 8, 2 times 8 minus 14 is, is positive 2. Squared, more positive, multiplied by 6, more positive. So is 7 a maximum or minimum value? No. Okay, so what did we show you? We showed that there was a critical point that was not a maximum or minimum value. Because this function is always increasing. Okay. For this one, find the limit, use L'Hopital's rule where it is appropriate. For all of these L'Hopital's problems, okay, you need to show every time you use L'Hopital's rule that it is either a 0 over 0 or infinity over infinity, okay? I remember from last year, people were not showing that and they were missing half the points on all these L'Hopital's problems. What do I mean by that? I mean that if I show this, limit as x goes to 1 of x squared plus 3x minus 4. What is the limit as x goes to 1 of this? 0, because I can just plug it right in. What is the limit as the x approaches 1 of this? 0. So this is a 0 over 0. So I can use L'Hopital's rule, right? You have to show that each time, or infinity over infinity. So that means that this is going to be the limit as x goes to 1 of 2x plus 3 over 1. Okay. Plug in 1, 5. Okay. How about this? I'll do a little video over the last 2 problems as well. Yeah, and I'll post that with it. Now that might be tomorrow. Okay, like that video might come out tomorrow because questions 13 and 14 probably not on tomorrow's portion of the test. Okay, so I might wait till tomorrow to post that video because I have like 0 time tonight. That make sense? All right. Study.
So 5